Hello guys, good day everyone. So today we'll be looking at electrostatics as well as capacitors. And like I said, I hope that we get to touch both of those topics today. Now, electrostatics is the study of charges that are at rest. Statics is talking about something being static means it's not moving. Electrostatics, so electro from the word electricity. So we're looking at electric charges at rest. That is called electrostatics. Now, of course, we know what an electric charge is. An electric charge is a property of a body that is responsible for electrical attraction and repulsion. Now we know that for unlike charges, they do what? They attract themselves. That means if I have even just like the same thing with our magnet, unlike poles attract. So if I have a north pole, let's say this is a north pole, and here is a south pole, what will happen is that there will be an attraction between them. There will be an attraction between them. So same thing, if I have a negatively charged object coming in contact with a positively charged object, there will be what? An attraction between them. So electric charge is responsible for the attraction or repulsion between what? Between bodies. Now, we now move on. Now, the charge of an electron, very, very important. Let's call it Q, is equal to 1.6 times 10 to the power of minus 19 coulomb. Though sometimes it's being given. So the charge of an electron is 1.6 times 10 to the power of minus 19 coulomb. And it is the smallest free charge in nature. Now, the next thing is that we'll be looking at methods of charging a body. That means charges are very, very important. We have the positive charge, we have the negative charge. So we need to know the method of charging a body. Now, the first method is called friction, charging by friction. Now, when we talk about friction, we're talking about contact. Friction is the opposition to relative motion between two objects. So when we talk about charging by friction, that means we are charging by rubbing objects together. So by rubbing them together, that friction, friction causes heat. As you're rubbing them together, a charge is being acquired by one of the objects. Now, a very good example is when you take a glass rod, let's say this is a glass rod, and then you rub it with silk. If you rub it with silk, which is a material, your glass rod will become positive by friction. So glass rod plus silk will be positive. Now, if you take an ebonite rod, and you rub it with 4, ebonite rod plus 4 will acquire a negative charge. Another one is a game we used to do them when we were little, that you take a piece of pen and you take a pen and you rub it on your hair, and then you now bring it near a piece of paper, very small piece of paper. What will happen is that you will discover that that pen will attract that piece of paper. And what's the reason? What's the reason for that? It is because your biro has acquired charge by friction. When you were rubbing it against your hair, it acquired some charges. A practical example of where this is being used is for petrol tankers, where you have the tanker, let's say this is the tanker being attached to something that rolls it, yes. Let's say this is the tanker. So what happens is that there are charges, are you getting me? There are charges that are acquired in the air, especially due to the dry weather. This is due to the friction between the air and the vehicle. So what happens is that as you're carrying that petrol tanker, these charges are rubbing on the moving vehicle. And if these charges are not being conducted away, it will lead to a spark. And because you're carrying petrol here, for example, that's very, very inflammable. And it will lead to an explosion. So what happens is that they will attach a chain here that will be touching the ground, so that as charges are being built up on the vehicle from the atmosphere, this chain will be conducting it away. This chain will be conducting it away. That's all on the first example, which is charging by friction. It is when you charge an object by rubbing it against another object, and then it acquires a charge. The second one is called charging by conduction. What is conduction? Conduction simply means that there is direct transfer of charges by touching. There is direct transfer of what? Of charges by what? By touching. Now let's take an example of conduction by charging by conduction. So let's say I bring two uncharged conductors. Uncharged means they don't have a charge. I'll bring them near an insulator. I'll bring them near an insulator to prevent the net flow of charges between them. So let's say this is our insulator. So both of them are uncharged. And I will now bring a positively charged metal conductor. This is positive, 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 positively charged. Now, if I bring it near two uncharged conductors, let me call it C and D. What happens is that all the negative charge in that metal conductor will flow to the free side of C, and all the positively charged part of it will be repelled to the free side of D. Now, what happens is that if I use this conductor, let me clean it now, use it to touch it. If I use this conductor to touch this material, since it is positively charged, what happens is that the free side of C will acquire negative charge, because negative and positive attract each other. So that's why this side, the free side of C, will do what? Will acquire negative charge in order to ensure this attraction, because I'm already using the positive charge to bring it near C. So here we acquire negative charge. While positive charge, in order to create balance, a positive charge will be acquired by the free side of the other conductor. Now, this one is not by rubbing. What happened was that here's a positive charges align with negative charge. So when I brought it near this my uncharged conductor, what happens? It acquired negative charge in order to keep a force of attraction here. And also, if here is negative, since it is in contact with this other ball, or this other conductor, which is uncharged, what happens is that this one too will acquire what? Positive charges. So that means I've been able to charge these bodies by conduction. These two are also in contact with each other. So just for balance sake, in this one, in order to balance the attraction between the positive charge, it will be negative. So also this other one will be negative in order to balance the attraction with this other side. So here too, what we acquire positive charges. So this is an example of what? Of charging by conduction. This is an example of charging by conduction. You bring a body near another one, and then there are exchange of charges. Now the next one is charging by induction. Now remember, by conduction there has to be contact. There has to be touching. Same thing with friction. There has to be touching. When there is friction, it is by rubbing against each other that the charges are acquired. While by contact or conduction, it is by touching each other that the charges are acquired. Now, the next one is called charging by induction, which is the charges are not being brought near each other. The bodies rather are not being brought near each other, but instead there is what? There is an exchange or redistribution. There's an exchange or a redistribution of charges. Now let me give an example before I go to an electroscope. Now a charged body pushes or pulls electron inside another object, causing a charge separation. Now this is an example of what? This is an example of charging by induction. Let me give an example. Let's look at how to charge a conductor positively. Let's look at how to charge a conductor positively through induction. So let's say we have a conductor, let me call it CD. So this is a conductor CD. This is an insulating stand. The insulator is to prevent net flow of charges. So the conductor, has no charge. So what I'll do is that I'll bring a negatively charged ebonite rod. Now this one is negatively charged, negative, 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 negative. Now, if I bring the negatively charged ebonite rod, let me call the conductor CD. If I bring the negatively charged ebonite rod near C, positive charge will be attracted to this point. Remember, positive and negative attract. So by convention, here will become positively charged, and the other side will become negatively charged in order to keep the balance, right? So for this to attract, here will acquire positive charge, and for balance, here will acquire negative charge. Now, what's going to happen is that, remember, I want to charge this object positively. So what's going to happen is that while the ebonite is still in position, I will stand on the ground with my bare feet and touch D with my finger. Now this thing is called earthing. It's called earthing. And when you do that, you are conducting XX negatively charged to the ground, negative charge to the ground. So this is the negative charge on one end. As I put my feet on the floor and I touch, that's my bare feet, and I touch the negative part of it, what happens is that this negative charge is being conducted to the ground. Let me call this the ground. So this negative charge will be conducted towards the ground, and after a while, I will remove the earthing conductor. I will remove the earthing conductor, which is this, and I will remove my ebonite rod. So what will now happen? That means all this negative charge will have been conducted to the ground, and this body will now be positively charged all through. So this is an example of charging by induction. Now, I did not bring my ebonite rod close to the body. All I just simply did was that I allowed there to be an exchange of charges. Now, since my goal was to get a positive charge, I now drained all the negative charge towards the ground. So that's charging by electromagnetic induction. Now, we'll look at what is called an electroscope. Now, what is an electroscope? An electroscope is a device that is used to detect and test small electric charges. Where is it here? Now, this is a gold leaf electroscope. It is used to detect and test charges. It's also used to test for the types of charges. We'll get there anyways. I'll show you a table. So it has a gold leaf, as you can see here. There's a gold leaf that converges or diverges in order to show the types of charges. So it converges or it diverges in order to show the type of charges. Now let's look at the behavior of the electroscope. Now when it is neutral, that means there are no charges on the electroscope, the leaves will be together. But when you bring a charged object, are you getting me? When you bring a charged object, the leaves will diverge, which is to spread apart. Are you getting me? Though, honestly, it is not a perfect method of testing for charges anyways. But for now, since it is according to what the syllabus needs, we are going to be learning how to use a gold leaf electroscope. Now, when you bring opposite charges near the leaf, what happens is that there's going to be a convergence. Convergence there is showing repulsion. Are you getting me? Convergence is showing what? A repulsion. Let me just give you an example. Let's draw a gold leaf electroscope. Let's draw a gold leaf electroscope. So let's say this is our electroscope. And these are the leaves. Let's put inside our metal jar. So if it is positively charged, now what's going to happen is this. If the charge on the cap is positive, are you getting me? And I bring a positively charged object near it, what happens is that there will be a convergence. Are you following me? That's to show repulsion. So that means these leaves, no, I cleaned the wrong thing. So that means that these leaves here would converge. That means they would tighten in to show what? No. This is a repulsion. So they will converge, they will tighten into themselves. If I bring a negative charge here, if I bring a negatively charged object here, negatively charged object near the cap, what happens is that it will converge. Are you getting me? Sorry, it will diverge. Diverge means to spread far apart. So it will diverge in order to show an attraction, not a attraction. Sorry. So it will diverge in order to show an attraction. So it is actually very simple to know the behavior of an electroscope. If the charges are the same, it will do what? It will, if the charges are the same, in order to show the repulsion, what happens? It will diverge. Wait, sorry, I hope I didn't mix it up. So in order to show repulsion, in order to show the repulsion, it will diverge, please, just in case. It diverges to show repulsion. Are you getting me? It diverges. Diverges means goes far apart. The leaves don't touch because it's the same charge. So it will diverge to show repulsion. But if the charges are the same, like in this case, positive and negative, it will converge, that's come together to show an attraction. So it will converge, which is to come together, and that shows an attraction. But now, here is why I said it is not a perfect way of measuring charges, because if the electroscope, for example, is positive, let's say it is positive, and you bring an object that has no charge, of course, no charge means that there will not be a repulsion. What will happen is that what? It will still it will still converge, to come together, to converge. Are you following me? If you bring a neutral body to it, that means the body does not have charge. What happens is that it will still come together and converge. So that means the convergence gives us a form of ambiguity. That means we don't know whether is it converging because the charges are similar. Because remember I told you, if the charges are similar, what happens is that what? It diverges, it goes far apart to show that, oh, there's a repulsion. If the charges are opposite, it what? It collapses. That means it converges. And at the same time too, if they have a charge or a body that is not charged, if they have a body that is not charged, what happens is that it still converges, it comes together. So that's why it is not a perfect means of what? Of measuring charges. But that's when the only time where it is kind of like unreliable is when there is an uncharged body. So we're not able to actually tell. Okay, so we're not able to actually tell. So let me still come again and draw a table for it. If you have a body, let me say this is a body and this is your electroscope. Let me call the electroscope E. Let's now see the effect on the leaves. What will happen to the leaf? If the body is positive and the electroscope is positive, what happens? That's no, we're not going to have an attraction. It's going to be a repulsion. So what happens? The leaf will go far apart, so it will not come together. So that means it's a repulsion. Repulsion. So that shows a divergence. Divergence means separate. Divergence means what? Separate. We're not touching each other. So I'll write divergence. So let me just write it. Diverge, or you get it. So if it is negative and positive, what happens? We're the same now. So convergence, which means that the leaves will come close. If I have negative and negative, no, we're not going to have an attraction between the leaves, right? Because both of them are negative, repulsion, which means the leaves will be far apart. So it will be a divergence. Now, at the same time too, if I have positive and negative, that means here is for the electroscope. If the electroscope is negative and this is positive, what happens? There will be a convergence coming together because they are opposite charges, so they will come together. Now, the issue is when you now have uncharged. So let me call uncharged 0. If it is uncharged and here is positive, what happens? It will look as though there's a coming together because there's no force here to cause a repulsion. So if it is uncharged, they will still converge. They will come together, the leaves. If here is uncharged and here is still negative, what happens? They will still converge. The leaves will come together because there's no reason for them to be what? To be diverging. Diverging means to separate, which means to show a repulsion. All right. So having done that, we will now go to Coulomb's law. We've looked at the behavior of an electroscope. We'll now look at Coulomb's law. Now, what does Coulomb's law state? Now, I've taught us gravitational field, and I said that Coulomb's law and Newton's law of universal gravitation are all called inverse square law. Are you following? They are all called inverse square law. Now, Coulomb's law states that the force of attraction between two charges, now these are its charges, is directly proportional to the product of their charges. Let me call it Q1 times Q2, and inversely proportional to the product of their charges. Now remember, in mathematics, when you bring in your equals to sign, there must be a constant. Now, so this is a formula for force of attraction between two charges, where Q1 is a charge on one of the bodies, Q2 is a charge on the other body, and then R is the distance between them, and K is a constant. And what is the value of that constant? It is 9 times 10 raised to the power of 9. You can get the unit through dimension, which is Newton meter squared per Coulomb squared. Newton meter square per Coulomb square. You can get it from here. If you make K the solid of formula, F is in Newton. So Newton times meter square will give me Newton meter squared, and divided by charge is in Coulomb. Coulomb times Coulomb will give me Coulomb squared. All right, so that's how we got the charges. So this is what Coulomb stated. Now the next thing is for us to know what an electric field is. An electric field is a region where a charge experiences sorry, I come again. An electric charge or an electric field. All right, so we were on electric field. So I can say an electric field is a region where an electric force is experienced by a charged body. You know, we talked about types of forces, and we talked about contact forces and non-contact forces, or you can call it the field forces. So the field force is a region whereby you can feel the effect of a force. Now, since this is an electric field, that means it is a region whereby a charge will experience the electric force. Just like for gravitational field, the gravitational force is being felt around the surface of the earth. So the field lines move from positive to negative. That's a convention. Though, actually, that's not how electrons move. Electrons move from negative to positive. But just for convention, the field lines move from the positive charge to the negative charge. So these are the positive charge to the negative charge. So the direction will be from positive to what? To the negative. Now, these lines are called electric field lines, and they are imaginary lines that are drawn in such a way that they show the direction of the field. Like for magnetic field, it moves from North Pole to South Pole. But we are not in magnetic field, now we are in electric field. Now, the negative charge is inward because it is receiving from the positive charge according to this convention. While the positive charge, as you can see, is outward. The direction of flow is outward. So that's an electric field. Now, the next thing is now an electric potential. Electric potential. Now, what is electric potential? The electric potential is the work done in bringing a unit positive charge from infinity to a point in an electric field. Now, when you bring a charge to your point in an electric field, you are bringing it from an infinite number of charges. Are you getting me? You are bringing it from an infinite number of charges. So the work done in bringing it from that infinity or unit positive or unit infinite number of charges towards a point in your electric field is called the electric potential. So the formula for electric potential V is equal to work done over unit positive charge. So V is work done over charge. Now, potential difference, that's where we get the term potential difference. It is now the difference in the potential between 2 points. Remember, potential, electric potential, first of all, is the work done in bringing a unit positive charge from infinity towards a point. Let's say this is point A. Now, it will take me a higher potential, you get me, to move it from infinity to another point, which is point B. So that means between A and B, there's what is called a potential difference. So B has a higher electric potential than A. So there will be a potential difference between A and B. Now let me come again. Electric potential is the work done in bringing a unit positive charge towards a point, let's say towards a point A here. Now, the farther you are, the more work I have to do to bring that unit positive charge to where you are. Now, between A and B, there's a difference in potential because B has a higher potential, which is more work done in bringing that unit positive charge there. A has a lower potential, which is lesser work done because it is closer in bringing it to a unit positive charge. So the difference between the electric potential between these 2 points is called the potential difference. And the formula for it also is still work done over what? Over charge taken. Now, like I've already explained that. There's something else I was supposed to talk about, which is electric field intensity, though it is not here in my slide. Electric field intensity. Now, electric field intensity is the amount of force per unit charge. Just like remember, gravitational field intensity is the amount of force per unit mass because it's acting on a mass. Electric field is acting on a charge. So, electric field intensity is force per unit charge. All right. So, another thing for us to look at is also electric discharge. What is electric discharge? Electric discharge is the sudden flow of electric charge through a particular medium. What happens is that when the charges become too much, the air can break down and allow current to pass. A very good example is lightning. In thunder and in lightning, for example, when charges build up in the atmosphere, it has to release some of them through what? Through thunder. Now, why you see lightning first before thunder is because light is faster than sound. So, like I said, lightning occurs when charges build up between the clouds or between the clouds and the air. And then when the potential difference becomes extremely large, there has to now be a sudden discharge of those excess charges from the world, from the earth. And that now brings us to what is called a lightning conductor. If you have seen a building before, let's say this is a building. This is a building. Let me draw a building. You see something at the top of the building, which is called a lightning conductor. Now, what happens is that those excess charges from the atmosphere, you can be hearing of your thunder containing even higher than 22,000 volts. So if that should run through a person, definitely that person is fried. That person becomes fried meat. So what happens is that there is a lighting conductor that is being put at the top of a large building because as a large building, you are closer to that atmosphere where there's a sudden release of electric charges. So what happens is the metal rod in that lighting conductor provides a low resistant path for the charge to flow towards the earth. They are being directed towards the earth. So instead of running through this building and causing a fire or electrocuting somebody, those excess charge that are being released by the thunder are being conducted by this lighting conductor towards the earth. Those excess charges are now being conducted towards the earth, and that protects the building. So our next subtopic is actually capacitance. So what is capacitance? Capacitance is the ability of a capacitor to store electric charges. So a capacitor itself is an instrument that is able to store charges and supply electrical energy when needed. So how does a capacitor come into being? You have two metal plates. If you have two metal plates and you now have an insulating material there, I told you that this insulator prevents the flow of charges. Unlike a resistor that just opposes, that means it limits the charges, an insulator prevents the flow of charges. So as these charges are being stored in these metal plates, you have an insulating material in between them, which is called a dielectric, that does not allow the charges to flow in between the two metal plates. So we now move on to the dielectric medium. Like I said, we have that material. The medium is talking about what is this dielectric made up of. Is it made up of air? Is it made up of paper? Is it made up of glass? Is it made up of plastic? So it increases the amount of charges that can be stored because instead of us having these charges flowing between the plates, this dielectric medium prevents that and enables the charges to be stored inside your metal plates. So Capacitance, like I said, is the ability to store charges. So capacitance, the formula for capacitance is quantity of charge per unit what? Per unit voltage. So capacitance is equal to Q over V. And the unit for capacitance is farad. The unit for capacitance is what? Is farad. Now the energy stored in a capacitor is given by half charge times the voltage, or you can say now Q itself from, before we had C is equal to Q over V. That means if I make Q the subject, I can have that Q is equal to CV. Let me clean this first of all. So from C is equal to Q over V, I can have Q is equal to CV. Now, since energy stored in the capacitor is half of the charge times the voltage, now Q is equal to CV. I can put it as CV, then times this V here. So it now be half CV squared. So any of this formula goes half QV or half CV squared. And since it is energy, the unit of energy will be what? Will be joules. Now, for a parallel plate capacitance, we have that the capacitance is dependent on some factors. So the capacitance is equal to permittivity times area all over what? All over the distance between them. That means if you look at this permittivity is the constant that shows how much permission does that material give for charges to be stored. It's called permittivity of the medium. Now, since it is a constant, that means capacitance is directly proportional to the area. So the more the area, the more the capacitance, because the more spaces for charges to be stored. And capacitance increases when the distance is lowered. That means if the distance between the plates is, small like this, your dielectric material is in between, more charges will be stored in between them. But if they are far apart, this is an inverse relationship. The capacitor is inversely proportional to the distance between them. So the more distance, the less capacitance. And also, the more the dielectric power or the more the permittivity of that material, the more the capacitance. So with that, we're almost done with the theoretical part. So what is now left is the arrangement of conductors in parallel or in series. It is kind of like inverse. Now, this is the symbol for conductors, two equal plates. Now, this is called series connection. They're just going in a series, straight line, that's series. Why this other connection here is called parallel. There's branching. This is parallel connection. So how do I get the effective capacitance between my connection? Now, if they're in parallel like this, total capacitance would be, let's say this one is 2 microfarad, and here is 3 microfarad. So for capacitances that are in parallel, that's this branching, what you're going to have is that you add them. So 2 plus 3 will give me 5 microfarad. 5 microfarad. But if they're in series like this, I have 1 microfarad connected to another 1 microfarad. Oh, sorry, I'm drawing something that looks like resistance. So 1 microfarad connected to another 1 microfarad. What you do is that total capacitance, 1 over total capacitance will be 1 over the first capacitance plus 1 over the second capacitance. Now, since both of them are 1, that means 1 over the first one, 1 over total capacitance will be 1 over 1 plus 1 over 1. Now, this will now give me 1 over effective or total capacitance will be 1 plus 1, which is the same thing as saying 1 over the effective capacitance is 2. Now I can write this as 2 over 1. So if I inverse this, because I have to get the capacitance, not inverse of the capacitance. So it will be capacitance over 1 is equal to 1 over 2. So capacitance over 1 is capacitance total, then 1 over 2. So when I'm taking more past questions, we'll be able to still practice this. So just for the purpose of a recap, if you have two capacitors that are straight like this, what happens is that you use inverse. Inverse of the capacitance total will be equal to, let's say this is 3 microfarad and this is 2 microfarad. So what you do is 1/3 plus 1/2. So this will be 1 over total capacitance is equal to, now find the LCM is 6. So this will give you 2 plus 3. So 1 over the total capacitance will be equal to 5/6. But remember, I need the total capacitance or effective capacitance. So I have to inverse this. So it will be CT over 1. So CT over 1 is CT. Then these two, since they're equal, if I do inverse to the left, I have to do it to the right. So it will be equal to 6/5. Are you getting me? So the effective capacitance will now be 1.2 microfarad. So that's all on what we need to know for JAMB at this level. So now I think we can just go straight to taking past questions. So let's go straight to taking past questions in this topic so that everything we have learned here can be put to good use. So I only take questions under electric cells, under electric fields, and then capacitance or capacitor. So let's look at some questions here. Okay, good. Now question 1 is not clear. They said if the equivalent capacitance also means total capacitance, but we can't find it. So there's no diagram there. So we have to discard that. Now question 2 says, why is it impossible? Question 2 says, why is it impossible for lines? Okay, wait, I didn't even talk about the properties of lines of forces. Now, lines of forces cannot cross themselves. That's one property. Like I told you that for electric fields, it flows from positive, let's say this positive to negative. That's just convention. So they don't cross themselves because positive moves in a particular direction and negative moves in a particular direction. Like positive is outward. As you can see, for negative, it is inward. Look at the negative. It is inward. So there's no way they will cross themselves because they have a well-defined path. Another property is that the closer the fields are to themselves, the closer the strength, or the stronger the strength of the of the field. So those are basic properties of electric field forces. So the closer that the lines of the fields or the lines of the forces are to themselves, then that means that the stronger the electric field. So those are the basic properties of lines of forces. So question 2 says, lines of forces do not cross each other. Now, what is the reason? What do we think the reason is? From what I just said, we can be able to get our answer. So, like charges repel each other. That's not really the reason why, right? That's not the reason why. Because like charges repel each other. Like charges are not talking about the lines of forces. B says a charged particle is deflected. We didn't talk about any deflection. Then C says like charges are arranged on the same lines of forces. No, each of them have their different lines of forces and their behavior. Then D says a positively charged particle can travel in only one direction at a time. True. Like the positive charge goes outward, right? So that's why even the negative charge also travels in one direction at a time. So that means that's the reason why. Now question 3 says an electric charge can be transmitted through dash. A says wood, rubber, and stone. B says paper, clay, and plastic. Now looking at it, wood is not a conductor, so it is out. B says paper, clay, and plastic. Paper is not a conductor, so it is out. C says glass, acid, and cloth. Cloth is not a conductor, so it is out. D says the human body, which is a poor conductor, but is a conductor anyway. C says water. I'm saying on D. D says the human body. Yes, the human body, water, and metals. Now, we know that water can conduct electricity, right? We have electrical conductors through liquids. That's your electrolysis, where they will dissociate into positive and negative ions. And metals are good conductors. So the answer to question 3 is actually D. Now we look at question 4, which says, which of the following is true of an electric charge? A says, positive charge means deficit of electron. Is that true? Yes, it is true. Just like from your chemistry. In a neutral atom, you have equal number of proton and electrons. So if I have 5 protons and 5 electrons, then that means that I am I'm having a net charge of 0, because positive charge is 5 positive and 5 negative. So plus 5 minus 5 is 0. So if I'm positively charged, that means, for example, maybe I now lost 1 electron. I'll now have 4 negative. So this will be 5 positive plus 5 and then 4 negative. So in total, we'll have a positive charge of plus 1. So that means it's showing a deficit or a reduction in the number of electrons. How did I have plus 1? I had to lose 1 electron. So A is correct. B says negative charge means excess of electrons. True. Because if I have 5 positive charge and 5 electrons, if I should gain 2 more electrons to my 5, I will now have 7. So this will now be plus 5 minus 7, which will give me a net charge of minus 2. So how did I gain this minus 2? There was an excess of what? Of electrons, which is also true. Wow. We have 2 correct options. C says electric current means the movement of electron, which is true. Like I told us, in an electric charge, current flows from positive to negative, just for convention's sake, right? So current is the flow of electrons. So that's also correct. Then D says all of the above. Then definitely the answer is D, because A was correct, B was correct, C was what? Was also correct. Now let's also solve question 5. Now I don't want this to be too long, so I'll cut it here and then I'll resume in another video. I'll resume solving these more questions. So I think I'll just stop at question 5. Question 5 says the total capacitance for the circuit above is dash. Now if you look at this, if you look at this, now I think this diagram is actually not correct. I think this diagram, I've seen this question before, so I think it's not. I think here is 2 microfarad, 2 microfarad. They will now have each of these ones in parallel, also being 2 microfarads each. Each of them being 2 microfarads each. So what's happening is that here is 2, 2, 2. 2 microfarad, 2 microfarad, 2 microfarad. Now, first of all, I told that once you have parallel connection, are you following me? Once you have parallel, that means there's a branching. As you can see, if it gets here, it branches here, it branches here, it branches here. What happens is that for capacitance, for resistor, it is different. But for capacitors, since they are all in parallel connection, what happens? You add all of them. So total capacitance for parallel will be 2 plus this other one, 2 plus this other one, 2. So to give me 6. That means the total capacitance for this parallel is 6. So if I'm to redraw this, I have this 2 here that is in series. Series means long line. With this whole 3 connections that are in parallel, they gave me 6 microfarad. So that means I now have 2 microfarad plus 6 microfarad now in series. I combine this parallel into 1. So it will be 1 effective capacitance, which is going to now be in series with your 2 microfarad. So now both of them are in series. So for series, what do you do? Total capacitance will be inverse. So inverse of 2 plus inverse of 6. So this now give me 1 over total capacitance is 1 over 2 plus 1 over 6. So the LCM is 6, which will give me 3. When you do that, this will be 6 and 2 is 3. So 3 times 1 is 3 plus 6 and 6 is 1. 1 times 1 is 1. So 1 over total capacitance will be 3 plus 1 is 4 over 6. So I'm looking for the capacitance, the total, not the inverse. I will inverse this to give me CT over 1, which is CT will be equal to, I'll do the same here, 6 over 4, which will give me 2 here 3, 2 here 2. So if I divide it, total capacitance will be 3 over 2 will give me 1.5 microfarad, which is option E. All right. So like I said, I don't want this video to be too long. There's something else that I missed, but I'll do that in the next video. Under the electric field, I was supposed to talk about the electric field intensity and the formula. But don't worry, in the next video, I would clear that up. So just watch out for part 2.